Okay, let me see it.
Yeah, I ended up doing some kind of weird trick for it, but it eventually turned out to give the right answer. So I'm going to hope that my process was actually correct because I have no idea.
Let me see cosine of 90. Hello.
Cool. What'd you share in there, Landon?
So the last problem from homework.
Sweet. Guys have any questions you were discussing amongst yourselves before I interrupted? So
Yeah, I am extremely unsure about the process I used to get to the answer. So the answer is 0. There's a lot of different ways you can get to zero that may or may not be correct.
yeah, that's a stupid question. It makes me mad. That's why would they make that so that it ended up at 0? It's kind of dumb. But I will show you something. Let's see, this is some new interface for Desmos here. Where's all my stuff? There we go. So watch this thing. What this is something I made in Desmos. It's kind of the, and I mentioned you guys we were going to start studying kind of the concept of how a piston worked, but so notice the dot that's going around the circle I'm treating as the driver. But do you see how the follower, the piston part of it, actually, there are times when it goes no speed at all. Actually, when it hits B for a second there, it actually stopped. And when it hits A, it stopped as well. And do you notice its speed is actually changing? It's not the same speed all the time. Like it depends, even though the rotational speed, kind of the omega, even though that's a constant speed, the follower speed or the piston isn't going the same speed the whole time. So it's not that it isn't possible to have 0 for speed. It's just that, you know, people are just learning this stuff. I give them a speed that kind of makes sense. But one of the things that's sort of not good about these problems is you're always asked to find something at an instant in time, but you sort of don't realize perhaps that that instant in time is just one of many. And so if I said, hey, what's the speed of that follower? Well, it actually kind of depends where it is. And to that end, let's see here. This is the, I don't know if this just feels right to you. Let's see, can I just move this thing where I want it to move? But if you think about it, over here, let's see. Does it make sense over there that although the driver is moving, it effectively isn't causing the orange dot to have to move left very much right now? That's effectively why it's not, that's why it's not moving much. In other words, it doesn't make a whole lot of difference over here. Whoa. It doesn't make a lot of difference over there. So the location of the blue driver, like if the location is there at what you and I would call 180 degrees, then it's actually not moving very fast. But I don't know if it makes sense to you, but if I move it here where that's 90 degrees right there, does it make sense if the blue kind of radius moves the driver a little bit now? It's actually moving the the green line or the orange dot that's following it the fastest possible. So actually it turns out its speed is the fastest there in the middle because the green line and the blue radius are at 90 degrees. When those are at 90 degrees, it's moving its fastest. And then as soon as it gets past this point and starts moving kind of the other direction, kind of that way, then it's actually slowing down until it at 180 degrees, it actually comes to a stop. And so I don't know if you can picture that, but that's just kind of cool to notice. So this concept of a snapshot in time, even though the driver is moving at a constant speed around in circles, and because it's connected to this piston by the green crank arm, the orange follower is going at a totally different speed. So it actually depends what the snapshot in time actually is. So what we're going to look at today is to kind of take this same thing and not just talk about relative speeds, but even talk about that green. So just stare at the green crank arm, for instance. Does it make sense it's rotating too? So we could actually talk about how fast one is going relative to the other. And we can talk about the rotational speed of that green crank arm, how fast it's rotating. And so that's kind of what we're going to do, is just take that to the next level. Do you have any questions about what you're looking at there? Unfortunately, in this, you can actually slow it down super slow, so you can actually see that happening, and also animate it. So let's see, what shall we talk about? Share screen and try to introduce this, what's called relative motion analysis. Again, that's a kind of a, I almost want to say useless designation, but last week we studied absolute motion analysis, where one thing moving caused something else to move. But this time it's going to be actually relative. 16.5. Let's get a fresh piece of paper. Let's see, share a screen yet. A fresh piece of paper and share a screen. So 16.5. The big word change here is relative. Motion analysis. So what is that all about? And I think the piston makes a good model. That's why I've been kind of showing you a lot about it and so forth, because it helps you kind of understand how this happens. So this is something I really want you to get your mind around conceptually, but I'm going to show you a formula. It's not going to make a lot of sense to you for a little bit. And I want to see if I can get it to make sense to you, because this is an example of something, if you read it in the book, you're going to go, I just do not understand what that is saying. So let's say we got this guy here, to keep using what we were using before. And I'll stick a point on it right there. And we'll cruise out here to a piston. And I'm going to try to simplify this as much as I possibly can. And so this will be what you just saw, except for I'm going to switch up what the driver is. And so we're going to say this thing right here is actually moving with a velocity. We'll call this A. And so this is going to be our driver. So I'll give it some velocity there. And so the question is, if I give that A a velocity, the piston's got a velocity to it, so it's kind of cruising to the right. Then, of course, it's actually going to cause B then to kind of move around in that direction, right? This is what B is going to have to do to follow. I'm making up my own language here, but the kind of the concept of the driver and the follower. And so if I, like in a car, if I had an explosion happen there inside that piston, and that caused velocity on the piston A, and then the crank arm took it over to the crankshaft, that's going to cause a rotation. In other words, a point a point where that crank arm is attached, it's attached at B, it's going to be spinning. And so that's kind of what we want to understand. And that's the idea of relative motion analysis. In other words, A causes B. A moves, well, then B is going to move too. But notice because B is constrained to be in the shape of a circle, that's kind of like linear motion being turned into rotational motion. And you know, rotational motion has like a linear velocity component to it. So, you know, what is that thing doing? Well, it's got kind of a velocity of B, which remember is actually tangent to the circle, but then it's also got kind of the omega of B as well. Like, you know, how many radians per second is that rotation causing and so forth. And so your reaction to that should be, frankly, confusion. Like, wow, how would you know that? You know, what is that? And what's going on there? I notice the particular location that I'm at right now. You know, it's not like that's at 90 degrees. So how does that really work? So what we really need then is a formula that kind of tells us the velocity of B is equal to what? You know, like, what is that velocity of B? And so here's the concept that I want you to kind of understand. The velocity of B, what is that equal to? Well, in order to make sense of this, because linear motion turning into rotational motion is just kind of hard to quantify. How does that, you know, it depends where you are on the circle. And, you know, it's like, how am I going to figure out what that is? And so let's consider this. I'm going to move this guy down here so he's out of the way. And I'm going to move this guy up here a little bit. So it really moves in kind of two simultaneous steps. See if you can picture this and interrupt me because I'm trying to make this make sense. It really moves in two simultaneous steps. One, what mathematicians would call a translation. Have you ever heard that term before? Translation is, well, if A is moving to the right, then does it make sense to you that kind of what's happening then is, well, B is moving to the right as well? In other words, if you just think of that rod as being kind of dragged to the right, and here's a bit of kind of cool terminology. If A is where it was now, then we'll call that A prime. And if B was where it was, well, then now it's B prime. In other words, if A was moving at, say, 5 meters a second, then B is moving at 5 meters a second. If it wasn't attached to anything, does it make sense that's what would be happening? So the absolute motion analysis, they're connected. A and B are connected absolutely by this rod. And so if you drag A 5 meters a second, then B is going to go 5 meters a second. Except for you say, well, that's not really what happens because B has to stay on the circle. Well, what happens second then is a rotation. So it sort of drags to this new position. But then in order to stay on the circle, now that the new center of the circle, the center of the rotation is at A prime, does it make sense to you that, I'm trying to draw a portion of a circle there, B really has to go to there, like B double prime? That's what happens. But it gets there in two steps, and they happen so quickly, you sort of don't even notice it. But it's almost like it goes inch to the right, rotates down, inch to the right, rotates down. But the cool thing about this is if we break it into those two steps, even if we say they're simultaneous, then we can actually just add those two together and say, what's B's motion? Well, it has a linear component, then it has a rotational component. So I'll see translation. matches A. And then the rotation really rotates around center A prime. So that's what I was attempting to draw with kind of those dotted circles. And so B moves effectively then, well, just like we said, it really just moves down to here. And of course, I drew it kind of large so you could see it, but realistically that would just move the tiniest amount. So what's the formula then? Well, how can the velocity of B found? Well, first it can be, you just say it's the velocity of C, whatever's, I'm sorry, A. Let's see here, what are you doing? So whatever A is, that's what B is going to be as well. That's the translation part. But secondly, you have the velocity of B with respect to A. So that is the translation. That is the rotation, because it actually is rotating in a circular fashion. Around that. Now, this is really our key formula. But the question is, first of all, is it sinking in? And then secondly, like, what? Let's play with it a little bit more. So let me make a copy of this down here, and I'm gonna just change some things about it. Because what you should be thinking right now is, I get the velocity of A matching over there. I get the velocity of A would match the velocity of B. I'm guessing that you're able to kind of track that. Okay, but what about the rest of this business? Type A person, got to get rid of everything. That was a mistake. Guess that one's staying. So I get the velocity of A, you should say. That's just, well, I guess we drew that like right there. It's exactly parallel. Since A is stuck aiming exactly right, then this would be the velocity of A up here. It's the same exact match. But remember, what's the velocity of B with respect to A? Well, that's where this kind of circular shape comes in. So I just want to kind of highlight that a little more to try to give you every chance I can to kind of go, okay, I see where that's going. Come on, man, let me grab that. There we go. So again, what is velocity of B around A? That's what that symbol is. Well, this is the circle on which it is rotating. That's the thing that I want to know if you understand. That's what it means for B to rotate around A. Well, where is velocity on a circle? I mean, if I'm here on a circle and you're traveling on a circle and there's where you are, unless you're going in that direction. If I said this is point C, where do you draw the velocity of C? Notice that's V, not W. Where do you aim that?
Just tangent the circle.
Exactly, tangent to the circle. Which is sort of code for at 90 degrees to the radius. Does that make sense? Those things are both true. So that's where the velocity of C is, right? That's where we say it is when it's on a circle. So over here, where do I aim? Where do I draw? I know where velocity of A is. I drew it in the picture, but where's velocity of B as it rotates around A or with respect to A? Well, it's perpendicular to the radius or tangent to the circle. So right here. 90 degrees. That would be the velocity of B with respect to A, or around A. That's where those two velocities actually are. So it's kind of like the point is just being taken and dragged right and then dragged back over here. And the end result is it was here and now it's there on the circle. But those are both actually straight lines. You see what I'm saying? That's what's so cool about this. Those are straight lines. And so we took this confusing curve motion and we said, hey, if we break this up into two parts that are happening simultaneously, then we can actually get that thing to cruise based on just a couple of velocities. And of course, if we want the velocity of B, it's got to be related to velocities, right? I mean, I got to add velocities to get it. So that's what you do. So it's like those two velocities are what I've got to come up with. If I want the velocity of B, I'm going to have to come up with those other two ones. Let's see. So at the risk of beating this horse to death, and maybe I am doing that now, I'm going to just quickly draw this in AutoCAD. And actually, I'd like you to tell me when we're done. That was a waste of time. I got it. Actually, I'd like to know. Or no, that actually helped a little bit. You're not going to hurt my feelings. You're helping future students. But this isn't going to take very long. So I'm going to quick through. So I'm going to rotate this thing into position now. So what do you do? Well, you first take it and you cruise to the right a little bit. So there's step one. There's velocity of A. Move to the right. Now what am I going to do? I'm going to say rotate. Watch this happen. I'm going to rotate around this point. And does it make sense if I rotated to right there? Now the point has moved from where it was to where it went next. You see that that's what's happening? And do you see which point around which I had to rotate it to get that to work? A second ago when we were spinning this, did you see that that green arm, if you will, was indeed rotating around this point over here? So you already had that, waste of time? That helped. I'm curious.
Mostly already had it, I think.
What about you, Ella? Totally fine with that.
I'm totally fine with it. I mean,
okay, so fine. What does that actually look like? And let's just play with that a little bit more. So that's the concept of our basic formula. So the only thing that's going to be weird is like, I use the letters kind of A and B this time, but as soon as I make up some example, it might have B's and C's. And so it'll take you a while to kind of get straight which one was which one went over there. And right now, as I said, the example that I just gave, the A was the driver and the B was the follower, but we have the same exact set of problems that work the other way. What if B was the driver and A was the follower? It's still the same, but it's just going to feel a little weird. So that's really what this week is about, is can we spend time to actually figure out how the motion of A causes the motion of B? How if we know what A is doing, then we can actually know what B is doing. That's kind of the idea. So let me just add one more thing to this statement up here, and then we'll just kind of wade into an example. We certainly want to get into an example as soon as we can here, because that's worth a lot more. So don't forget a couple of things you already know. Let's see if I remember right. V is equal to omega times R. Like that's how you get from linear velocity to rotational velocity. That's a pretty important formula, right? And incidentally, what this really says, I don't know if you think of it this way, but linear velocity and angular velocity are proportionate to each other. And the proportion is radius. Like the radius is what allows you to convert between those two worlds. And so since the since that second one is really a rotation, does that make sense? Since that second one is kind of a rotation, kind of a circular motion, if you will, in a sense, it almost makes maybe a little bit more sense to replace it with omega times r, so to speak. In other words, I'd have to know the length of the crank arm, connection rod. So it's also possible to write it that way. So I don't know if I should rewrite this, but I think I will just quickly. So velocity of A plus the rotational speed of B around A times the radius of, I guess I'll just say AB, like the connecting rod AB. So in a sense, that's another formula that I could have here if I wanted to. Now, let's see what's sitting in the note sheet about this for you guys to steal in the next test. Wow, that was lucky. Exact same letters even. So velocity of A is the translation of B due to the motion of A. Velocity of B around A is rotation of B relative to A. So, okay, that's in there. And then I kind of drew a picture over here. So one thing that's in this picture that I didn't add a second ago is the real velocity of B, notice, is, well, perpendicular to the circle it's on, right? Isn't that the actual velocity of B, which is what we're trying to find, right? So don't forget about that. If the problem is, basically saying, what's the velocity of B? I know what velocity of A is, it's 5. What's the velocity of B? Remember, the answer to that question is, well, perpendicular to the rotation of the circle, because remember, those two things aren't actually happening. It's simultaneous. It's not like it slides to the right and then rotates down and slides to the right and rotates down. So the real velocity of B is actually perpendicular. So, where are the other ones? Well, A is right here. It's the velocity of A. If it's aiming right, it's going to pull right. Velocity of B with respect to A, as I said, is perpendicular to the radius around which it's rotating. And so, wow, that's kind of cool. It's kind of confusing. Well, let's see how you do. Let's bring in our first question, which is very similar to this. I tried to kind of make your first question, if you will, an exact match to the same problem. And these are all my homemade questions that I think are much clearer than the book. So these are my AutoCAD drawings of this. So notice I didn't just draw A in space, like I actually drew it like a piston, in the sense that A is constrained only to move right and left. Can you see that? Like that's the way a piston would work. So if I drag A to the right, that's the only way it can go, is right and left. And so I'm putting, as the driver, I'm putting a 3 foot per second speed on it. And notice the snapshot in time right now. Notice where B is. B is at a very convenient place for our first problem. It's sitting over there perfectly level at 9 o'clock, at 180 degrees, whatever you want to call it. It's in a nice location. And so I'm basically saying at that snapshot in time, what's the velocity of B? So notice I asked a bunch of things. Find the angular velocity of link BC. So in other words, really that's kind of like omega down here. What's the angular velocity of that link as it spins around, or B? I could have just said the angular velocity of link. I said links BC, or I could have just said or B. What's the angular velocity of B? How fast is it going? I could ask that question too. But then I also said AB. Like, does it make sense? AB is kind of rotating as well, one way or the other. AB is rotating. And so that's the two questions that I have. And so I said, let's do all of that at the instant shown. And I told you that instant happens to be based on where A is and where B is and so forth. I told you that instant is when that's 40 degrees, and I give you a few lengths and so forth. So, okay. Now, conceptually, just staring at this, if I was to kind of take A and slide it to the right as shown, you probably can appreciate B is going in this direction, right? That's where B is going. It's going in that direction. obviously. And notice that happens to be straight up and down, which is wonderful. Usually B is at some weird angle, right? That has like an X and a Y component. That's straight up. Whew. That's really neat. 1 second later, it's going to be over here and velocity of B will be going in that direction, and that'll be more complicated. But right now, the instant in time, super simple. Okay, well, here's the thing. And I'll throw this quickly just on this previous page, just because we're about to do it. And it seems like this was the introductory page. And so we must consider horizontal and vertical separately. And in reality, this is kind of what we were doing with vectors. Like we took vectors that pointed at some angle and we just said, let's just break them into X's and Y's every time. And the same thing is really kind of true here. So this is an important point. You can't just kind of do this all at once. So let's go try to do this. Let's see. So let's see, A is cause this one matches the note sheet. We got sort of lucky. So A is the driver. Therefore, our question really comes down to what's the velocity of B? And we said that's the same as the velocity of A plus the velocity of B as it rotates around A. That's really our fundamental formula. Great. And so let's take a look first at the horizontal. And I just picked that randomly. Is that a good choice? Should I have done vertical first? I don't know. You need to do both. So let's just figure out what's going on. In other words, the equation, the fundamental equation here is not velocity of B, but velocity of B in the X direction. It's not the velocity of A, it's the velocity of A in the X direction. And it's not the velocity of B as it rotates around A, it's the velocity of B as it rotates around A in the X direction. That's all we're looking at. So the question is, do I know any of those? So in the picture, notice it's obvious that A is moving at a constant speed to the right of 3 feet per second. So that's what the velocity of A and X is. Notice the velocity of A and Y is 0. It isn't moving up and down at all. So we'll get to that in a second. And notice I'm maybe really happy, if you will, that the piston wasn't moving in this direction, right? Because then I'd have to modify it by the cosine of 30 or sine of 30 or something like that. But we're going to get there. Like you have to do that at some point, but let's just keep this simple. So that really is 3. Do I know anything else? You actually know at this instant in time, what direction is the velocity of B going? It's going straight up. So how is it moving in X? How is this thing moving left and right since that's X? It's not moving at all. So again, did we get really lucky there that was going straight up and down? Yes, we did. Otherwise, we wouldn't have been able to put a number to this. I'm curious, could you draw the velocity of B as it rotates around A? Could you draw that in this picture? Like, do you know where to draw that? Well, remember that if it's rotating around A, then it's rotating on the circle with A at the center. And so perpendicular to that arm right there, 90 degrees right there, that's the velocity of B with respect to A. So it's like important to know where these things are. Like you have to conceptualize this and draw this. So if that's the case, if that's kind of like the hypotenuse of this, then do you agree that that is the velocity of B with respect to A in the X direction? And this would be the velocity of B with respect to A in the Y direction? Do you agree with that? So that's interesting. Let's come back to that in a second. What about vertical? Well, it's no different. It's rewriting the formula. The formula that runs this system, but then just saying, oh, vertical, huh? All right, Y values. So I'm going to get two equations, two unknowns for these problems. Now, in our case, we don't have to work quite that hard, but again, let's just kind of throw in what we know since we drew the picture correctly. So what's the velocity of B in the Y direction? Well, in this picture, notice it literally is the velocity of B because it is entirely in the Y direction. Notice the velocity of A, as I said a second ago. What is it doing in the Y direction? Well, it's moving right, which means it isn't moving up or down at all. And I don't know. Basically, I don't know anything else. I don't know the velocity of B with respect to A in the X direction. I don't know it in the Y direction, and I don't know the velocity of B. But these are my two equations. And of course, what you should say now is, hey, I do know, thanks to that first horizontal equation, in a sense, you could say we got lucky. Does it make sense that you know right now that this must be -3? Because those have got to add up to 0. Notice that fits the picture. It's saying actually that thing is moving left at 3 feet per second. At that moment, only at that instant in time. It should bother you a little bit. What do you mean? You're saying it's connected? You're saying it's connected up here and moving right, and somehow that's going to cause this to move left at the opposite speed? Yes, but only for a billionth of a second, and then it's going to do something different, if that makes sense.
Hmm. Yeah, it feels weird. The exact point makes sense, but it just feels kind of odd.
Yeah, that's exactly why I pointed out, because it feels odd to me too. But remember, that's kind of a rotational speed, if you will. And that's only in the X direction. Now, if you look down at the kind of the second equation, the vertical equation, notice that's not so helpful because there's basically two unknowns down there. It's like an equation with only two unknowns, and the velocity of B, the velocity of B with respect to A in the X direction, -3 that we just found a minute ago. It's like it doesn't go down there. So it's like not super helpful. Well, let me show you kind of maybe a better way to think about this that'll work for future problems a little bit more easily. Based on this picture over here and the fact that this angle, we were told, the snapshot in time, or where the piston relative to the crank is and so forth is when theta is at 40 degrees. So that angle is 40 degrees. And then I got this right triangle over here and I'd like to get over there. So if that's 40, would you agree this angle would be 50? Because I'm going to erase this, but this angle right here is 90 degrees. That's the definition of that. That's what it means. That's why the velocity of B is where it is, because it's perpendicular to that radius. And that would mean this angle is 40 degrees as well, which means that this angle is 50 degrees, or that angle up there is 40 degrees. You can kind of pick whatever you want, but that 40 works its way over into our triangle. I'm going to use that 50-degree angle just because I like the look of it. I don't know why. Would you agree that, if you will, then, if that's the case, then another way to write this would be to say the velocity of the x direction would be the velocity of B with respect to A modified by the cosine of 50 degrees. I'll show you, maybe you'll see in a second why I'm doing this. If that's the case, then down here, I could replace this with the velocity of B with respect to A, but it'd be modified by the sine of 50 degrees. And now these match. In other words, they're the same exact unknown. Does that make sense? Not only that, I never wanted to know the velocity of B with respect to X and with respect to Y. I actually just want to know the velocity of B with respect to A. I mean, that's what this is actually all about right back here, remember? I really didn't want the X's in it. So notice now that I have this, I can kind of solve the house of cards. So I now know that the velocity of, so I could say, hence algebraically, velocity of B with respect to A cosine of 50 degrees has to be -3. And then if I bust out my machinery and divide that, -3 divided by the cosine of 50, I get -1.93. I was going to say meters per second, but it's feet in this problem. And again, I've kind of forgot what it was I was supposed to be figuring out. So I'm just kind of circling that or highlighting that, saying that's an important number. Now that I know that, I can of course put it down into the bottom one. So that means the velocity of B is equal to velocity of B over A sine of 50, but we just figured out that that was -1.93. So what is that number times the sine of 50? So that means the velocity of B is about -1.48. Anything wrong with that? Feel okay?
Why is it negative?
Yeah, does negative make sense? I always stop and make things make sense. Yeah, that bothers me. Let's think about that for a second. Yeah, that's bugging me. It should be positive, shouldn't it?
Hmm.
Maybe I'm doing something wrong, but when I'm trying to solve for VBA, I'm getting negative 4.67.
Yeah,
I'm typing something wrong in it.
what am I? Let's see. Oh, actually, yeah, I've got issues here. I looked at what I typed in my calculator. I'm sorry, and I didn't to solve this up here. I just did something stupid. To solve this up here, don't I have to divide by the cosine of 50? For some reason, I have -3 times the cosine of 50, so I managed to not even type it in right. So yeah, this should be -4.67. Sorry. So that number times the sine of 50, get -3.57. So that doesn't take away the negatives.
Yeah.
Generally, when I get a negative sign, I think that means I chose the direction wrong.
Well, in this case, we pretty clearly know how it's going.
Yeah, so I'm pondering that still. Because it like velocity of B is clearly straight up. We treated it like it's straight up. I used the conventions that up is positive and right is positive. It wasn't like I messed with the conventions of this.
Hmm.
I don't know. Numbers are right. Let's play with this a little bit more and maybe I'll come up with a good answer for that. So let's see, did we answer the questions? Find the angular velocity of link BC. Did we find that angular velocity of link BC? No. Did we find the angular velocity of link AB? No. We found these two linear velocities, but not the angular velocities. The question is, do you understand what to do with those? And not only that, which one is which? So let's stare at this picture for a second. If I want to know what this link here is doing, link BC, in other words, how fast is that rotating around? And again, the only reason we're talking about link BC is just to give it to something to stare at. We could just be talking about the angular velocity of point B. Well, because point B is rotating around C, then this is the velocity we're concerned with. Does that make sense? And this is the radius we're concerned with. Since the conversion between velocity and angular velocity is V equals omega times R, then we need this to be for sort of the B We need this to be the velocity of B, and we need this to be the omega of B, and we need this radius to be AB. In other words, B is moving, yeah, but around what point? Oh, around A. Well, then that's the length of its radius. And so we were told that radius was 7. No, that's wrong. BC. BC. I wrote the wrong number. It's not AB, it's BC. Gotta be looking at the picture. B is rotating around C. So we were told that was a distance of 2 feet. And we figured out a second ago, fortunately, that the velocity of B was negative 3.57. So now I know how to solve omega. I divide by 2, negative 3.57 divided by 2. So I get like negative 1.79. So that means the omega for B, or whatever, AB. In other words, is the point rotating? Is that what we're looking at? Or are we looking at the arm AB? Same thing. What would the unit for that be? Stare at your units over here if you want to know. If you divide 2 over there, you're dividing feet divided by seconds divided by feet, which means this is nothings per second.
So radians per second?
Second, which means they are radians. And so again, it's just weird to say nothing. So we say radians, but then it makes it look like the unit. And then again, it's a question of clockwise, counterclockwise. I'm a little trouble with this because I look at that picture and I think, isn't that moving? Well, wait a minute, maybe that is the right answer, because isn't that negatively rotating? Isn't that rotating in the clockwise direction, which is negative? So maybe maybe that's right. Maybe that means velocity of B really is negative 3.57. But again, I'm troubled by that because I'm thinking, isn't up positive? But again, we saw this arm AB over here was also rotating. And so isn't that cool that we can actually talk about its rotational speed as well? Well, since we're talking about, AB, then the radius of AB comes into play, because that's going to determine how fast it rotates, how long it is. And we were told that was 7 feet. And the velocity that goes with its rotation, is this B over A velocity. Because again, they're perpendicular. They've got to be perpendicular to each other to be kind of talking to each other. The radius of rotation around A is 7, and its speed has got to be perpendicular to that. So that's going to give me access to what I need. Same exact formula. So for AB, I have the velocity of B with respect to A equals omega of B with respect to A times the radius of, you could say B with respect to A or AB or whatever. It's just 2 points. And so this was 7 feet. And again, we went to all this trouble a second ago and calculated negative 4.67. So I'm just dividing by 7. It's going to be a pretty small number. Notice how much of an effect the radius actually has. Negative 4.67 divided by 7 is like 0.67. So omega of AB, or as I like to say, B with respect to A. Your book won't say that, by the way, it just says AB. But I like to think of it as rotating around, B is rotating around A. But the reason it doesn't matter, watch my pen really quick. If you're looking at me and I rotate this right now, what just happened? Did I rotate this point around the other one, which didn't move? Or was it actually this one around that one? Does it make sense if I move them simultaneously relative to each other? It actually doesn't make any difference. So that's why the book will just say rotation. It'll just say of AB, like it doesn't even make any difference. But I just have a hard time visualizing that. So I'm just trying to help you do the same. So, and to that end, I want to go back and fix something up here. Like in this top one, we said omega of B as though B was by itself. But if B was rotating, it's not around A as I wrote here. This isn't true. It's around C. So B was rotating around C. That just adds a little bit more information. Instead of just saying B is rotating, it's like, well, yeah, it's rotating around C. I should have been a little more careful in what I wrote there. Now, again, I find this just, we'll take time to do one more example to give you a chance to soak this in a little bit more, but I find this cool in the sense that, wow, we're able to, actually figure out what happened at the follower end. We had the driver end up there at A moving to the right, and we know exactly what's happening at the other end. That's really cool. But remember, this only applies for a billionth of a second, because as soon as it changes locations, we're going to get a totally different speed. We're going to get different rotational speeds 1 second later. So it's like, man, that's a lot of calculations just to know what happened at an instant after we do it all again 1 second later.
Yeah, and this example is making it pretty easy for us by having it be just the starting position be really convenient.
Yeah. And so let's take it up a notch and do one that isn't in the same position, that isn't in such a nice position. See if we can tackle that, and then we can say we're okay for the day. So find the velocity of C. That's interesting. So that actually means that we're doing this one backwards. The driver is actually at B. I noticed this time I actually took the time to sort of draw in, because the dotted line that you see right here is just representative of, because of this link right here, because of that link, B is going to have to stay on this circle, but it's not like there's a circle there. Does that make sense? If I don't draw that circle, then this is really confusing, but it's not as though there's a circle there. I guess that's kind of what I want to make sure you understand. So this time B is the driver. And what do you know? Well, you're given that the rotational speed, notice I even worded this nice, at least the way I consider it to be, to make some sense. I said the rotational speed of B as it moves around A is 2 radians a second. And I said it's in the clockwise direction. And so in the sense we were given 2 radians per second. Notice it doesn't have an acceleration. It's just, that's its speed. It isn't changing speeds. And I also know that BC is a length of 10 meters. And I know that the radius AB is a length of 4 meters. So I'm just going to kind of squeeze those in there really quick. And so B is basically going in this direction. And notice I'm very careful to draw this at 90 degrees right here. That's the velocity of B. It's really going in that direction. So isn't that going to cause this guy to move to the right? Isn't that what the velocity of C is going to look like? It's not going to go left. It's going to go right. True? And notice it's constrained to move left and right, which again is pretty nice. It doesn't get to move up and down, but it's constrained to move left and right. Notice though, in this case, the relative position of things is a little weird. You notice B is not like right at 90 degrees or 270 or 180 or something. It's in some weird location. And notice that weird location is 65 degrees. And even the other one is in weird location at 35 degrees. And so, okay, great. Now, notice I got the letters all screwed up. Like before, my formula was A's and B's and so forth. But let's see, what would the formula look like? Let's try to get this by logic. Well, I know what velocity of B is doing. What I'd like to know is the velocity of C. Like that's the thing that goes over here by itself, is what's happening to C. It's the follower, right? And that's what I'd like to know. The follower. It's the follower. So it makes sense that that'd be the question. And we say, well, that's the same as whatever it's doing up at B. whatever B is doing. So that's the translation part of it. Plus, now here's the part that's confusing. Is it velocity of B with respect to C, or B around C, or do I have it upside down? Is it C around B? Again, I need to be able to visualize this if I want to get this question right. Which one is it? Because I just kind of threw those two out there. Well, let's play with that a second. Would you agree that since B is perpendicular, that this is actually the this is actually the direction that B is moving right now? It's moving up at a weird angle up in space. And if that's the case, would you agree that, I may have to erase this because it might make a disaster, but would you agree that a second later, that's where C would want to go? Like that's what this part of the statement says right there. Do you agree with that? B is moving up and to the right, so C is moving up and to the right as well. Now, because of the constraint of the piston down there, is it actually going to move up in the air like that? No. Simultaneously, there's going to be a rotation. Do you see where the rotation is, though? You see which direction it goes? So C is going to have to rotate. So it's actually the rotation of C around B. Do you see that? And so in order to stay in the cylinder, do you actually agree that perpendicular to that, this is actually the velocity of B. I'm sorry, I wrote that backwards. That's the velocity of C as it rotates around the fixed point B up here. Isn't that weird? Like you might not have guessed that it, if you will, rotated in that direction. So I got the formula right now, but I didn't just cheat and use the note sheet. And it frankly would have been hard because the letters didn't match up. You know what I'm saying? And also because it's backwards, like the driver this time is the spinning one, not the cylinder one. And so you see how hard this can kind of be? So, okay, I think I got this now. Well, actually, let's do one other thing here while we're at it. Can't we actually know the velocity of B, the actual velocity of B? Can't we know what that is based on the formula omega times r? Since we know omega was 2, and since we know the radius of that was 4, and are the units screwed up? Radians per second, and 4 was meters, so it's meters per second. So it's 8 meters per second. So that's kind of cool to know. So I actually know what, I know that, but again, notice it's in a weird direction. That's the thing that's not cool about this. So now let's set up our horizontal and vertical equations. And this time I'm just going to kind of write them out and not plug anything in, but let's just see if we can kind of get them going. So horizontally, and again, all I'm really doing is just saying, well, let's rewrite our equation. Velocity of C equals velocity of B plus velocity of C with respect to B. I'm just writing those equations. The only thing I'm doing different is coming back and saying, we're talking about X, we're talking about X, we're talking about X, we're talking about Y, we're talking about Y, we're talking about Y. So now I just want to kind of plug in stuff that I know. Well, notice 8 doesn't go anywhere. I can't put 8 anywhere. It's like the sort of the one velocity and I know, and it goes nowhere. What do I have to do?
Break it into its X and Y components.
Yeah. Got to split it up. And notice somehow I got to figure out what angle is going on up there. Well, maybe you know, since we were told theta, the snapshot in time was 65 degrees up here. Maybe you know that that means this angle right here is also 65 degrees. Do you agree with that?
Mm-hmm.
And since this angle right here was 90, then 65 and 25 makes 90. And so that's my modification. So, okay, I can at least go down and talk about the velocity of B now. So the velocity of B with respect to X would be 8, but modified by the cosine of 25 degrees. And notice it's aiming right, and I'm calling that positive. So far, I think I'm cool. And so that's the velocity of B in the X direction. And then this would be the velocity of B in the Y direction. And that's also positive. And that, of course, would just be 8, but modified by the sine of 25 degrees. So at least those are known numbers. So that's good. I'm certainly not there yet, but at least I know that. But now I've got to come down here to this bottom one and say, what's going on down here? Well, velocity of C with respect to B. As I said, it's really rotating. Now I'm gonna go back and kind of redraw this now. I drew that, if you will, so that you could see it happening. It's 2 pieces, but we really got to draw this simultaneously, right? Not as though it's actually moved. So let's go back and get rid of all this and see if we can conceptualize that simultaneously. So what we learned is this is actually the velocity 90 degrees to the rotational arm. This is really the velocity of B. Sorry, the velocity of C with respect to B. And now that we know, or we're told that the snapshot in time that this is 35 degrees, I know that since this is 90, I know that this is 55 degrees, 55 and 35 is 90. But then I also know that this is 90. So that means that angle right there is also 35 degrees. And so 35 degrees will be my modifier. So I'm going to do what I just did a second ago and say, well, I have velocity of X and velocity of Y, and that's 2 different variables. But rather than 2 different variables, I'd really rather just have one. And so couldn't I say, well, whatever this is, it's the velocity of C with respect to B, but since that's horizontal, that'd be modified by the cosine of 35 degrees. And similarly, wouldn't this also be the velocity of C with respect to B, but modified by the sine of 35 degrees? And by the way, do you agree that since this arrow is aiming down, the velocity of C with respect to B is actually right? In other words, this is a positive number, whereas this is actually a negative number. Does that make sense? So again, I got kind of a negative problem here. So I'm wondering, should I throw a negative in there saying it's negative, or will it just come out negative on its own? These things are problematic. Let's just leave it alone for a second. And so I'm still sort of sunk in the sense that don't I have, well, up here, I have V of C with respect to X. I have V of C with respect to B. This has got 2 unknowns. This has also got 2 unknowns, but unfortunately, they aren't even the same. Well, these are the same, but this is CX and this is CY. So I've actually got 2 equations and I've got 3 unknowns. Do you see that? Do I know anything else that I haven't gotten involved?
Well, we know there's no Y component of V sub C.
Exactly right. Is C allowed to move in the Y direction because it's in a horizontal cylinder? The answer is no. And so that's my window. That's my way into this. Because it's constrained to move right and left only, I can say that's 0, which means I can now look at that vertical equation and say, oh, cool. Well, I can actually solve for the velocity of C with respect to B now. So let's see, if I punch buttons, I subtract 8 times the sine of 25 over to the other side, and that's a negative number. It's over there, but then I divide by the sine of 35. And I get negative 5.89. This needs to stand out a little more. And in this problem, I didn't leave units in it, but in this problem, we have meters and seconds. And so that's, again, I don't even remember, like, I don't even know what this problem was asking. Is that like in my world, a boxed answer? Or is that just like one of the things that I'd like to know? So I don't really know what to put around, but at least I should highlight it somewhere. And just say, yeah, that's important. As I figured that out. And now, of course, I could actually go back up here and throw that in there and multiply it by the cosine of 35, and then I would have the velocity of c with respect to x. So that's kind of cool. So velocity of c not with respect to x, but in the x direction. So I take that number times the cosine of 35, and I get negative 4.82. .828, so negative 4.83. Feel like I put out something. Actually looking at the answers I had last time when I did this now for the first time and seeing them not getting the same answers, which makes me think I did some similar stupid thing to what I did last time. So I'm just staring at that for a second and seeing if I can find out what it is.
I got 2.42.
Yeah, that's about what I got too.
Is that the right answer?
No. So the 5.89 is right. At least that's the same answer I got before. Again, this is good to talk about because it just illustrates it's easy to type things in your calculator wrong. So I'm just kind of re-looking at what I looked at. It's hard to check your work. It's because I've done this more than once. At least I have something to look at. Oh yeah, I just that was dumb. I didn't even include this number at all. Like I just left it off like it was 0, like an idiot. So yeah, so we got to stare at this a little bit because here's a place where the sign comes in and matters a lot. So if that comes out negative, if this number comes out negative and this one is positive, then they're gonna, it's like 5 and -2. They're gonna make 3. If it's 5 and +2, it makes 7. So the sign makes a big difference. So let's just stare at that a little bit. Is there any reason? This is again why we're a little bit worried about signs. So we set up here, these certainly, I'm just thinking out loud with you here. These certainly would both be positive, right? Because B is pointing uphill to the right. But down here, the right triangle, velocity of C would be positive, but this velocity here, this would be negative. So the question is, should I be, so is it good? So one of the confusions of this is this, should I call this a negative number right here? I guess I want what do you guys think? Do I want to call that a negative number? In other words, I kind of have no trouble with right being positive and down being negative and so forth, but this is just kind of going in that direction,
Well,
then do I think of that as negative? Because now all of a sudden it's not going in either direction, right?
I
That's-
called it negative.
I mean, in my case, I called it negative just because I let math take its course. You see what I'm saying?
What is the right answer supposed to be?
I'm looking at what I did last time and I got 12.08, but I'm actually doubting it. And the reason I got that is because I didn't call this negative. Does that make sense?
yeah.
And I'm actually embarrassingly doubting that. Like I'm thinking, because this is so hard to visualize that you kind of want to be careful about, you know, what method are you using? Are you just going to let signs take their course, or are you going to, you know, just draw right triangles and insert them yourselves? That's kind of the issue here. So I'm thinking out loud here, but I'm thinking, okay, well, that comes out negative. That's not moving. Eights, that's definitely positive. I mean, that has to be negative. 7 to 35 is a negative. I mean, it seems like that has to be negative. So the question is, if I, you know, put negative 2.42 in there, which is kind of the right answer, does that make logical sense? And the problem is the answer to that is no. Do you agree with that?
Yeah.
It's moving to the right.
Huh.
You see what I'm saying? Not moving to the left, so doesn't make sense.
It's this whole chapter. Science seems to be kind of scary
Yeah.
thing to be looking at.
Well, and I will tell you, like, I have a personal problem with this because I'm a sense making kind of person. So I have a hard time not just reasoning these things through for myself, like drawing pictures and so forth.
Why we got negative again? Negative 2.42.
Well, we agreed that this 5.89, based on the algebra down here, because this number is certainly positive, then that means this number has to be negative if they're going to add to 0. So based on the algebra, this would want to be negative. Well, if we leave it negative and throw it in up here, that produces negative 2.42.
I got it positive.
Is it positive 2.42?
Yeah.
Hmm.
Wait a second. Yeah, I got it positive.
Oh yeah, it is positive.
Oh yeah, what the heck? I
So-
swear to God, I got negative just a minute ago.
So, yeah. I thought I did. So that's positive. So I think we're okay.
All right, I guess it does make sense somehow.
But remember, the same thing happened on the first problem. We weren't super happy with it there either. I mean, I'll tell you what feels better to me is to say it's stupid to call this number down here negative. Let's just call it a speed, because all we really care about is its X and Y components, right? And so if I come back over here, whatever its speed is, and I just assign, I assign this to be a positive and I assign that to be a negative based on the clear physics of the picture, then it seems like everything would work out right. For instance, this number right now, so I'm just thinking out loud here, but velocity of, would you agree that because that's a Y, this needs to be a negative answer? that make sense? Because it's down, right? And that's what happened for us. The only way that's the case is if, so that's good. I think that's working. So yeah, I think it is 2.42. Even though I would say I kind of don't care. I don't care what the sign of logically, the sign of, and by the way, this is an argument I've had in class every year. Like there's one of the reasons I'm thinking out loud with you about this is because it's different for every person. I had people say, that's stupid. Like you shouldn't have to think about this. Like set up a coordinate system. And if you call right positive and up negative, then just let the signs take care of themselves. And there's an absolute argument for that. But I just find myself wanting to go, wait a second, I want to make sure I understand what's happening here. Why is that number negative? Does that really make sense? I think that's important. Anyway, you don't owe me any homework for this yet. Let's quickly finish this and get out of here for today. Because notice the problem actually asked, or the interesting part of this is, so find the velocity of C. We did that, but then also the angular velocity of length BC. In other words, since this thing is having to turn, since we drew this arrow in this direction, since this thing is actually rotating, again, I like to call this C as it rotates around B. That's the other part of this that's kind of cool to be able to answer. Do you agree with that? The real question was just what happens to C? We found it. It was 2, right? But it's also kind of cool to think about how fast is that link rotating at this point. So of course we can get at that, because the reason we can get at that is because we know this equation again. And so we found the velocity of C with respect to B linearly. We found that to be 5.89, and technically I think we're saying it's negative. And we know the radius of AB, CB, because we were told CB, we were told was 10. I wrote that in up there, so we know that's 10. So I just have to divide that. So that means omega is 0.59 radians per second. But again, let's just take a second. Is that negative or positive? So if I leave the signs in it, it should come out negative. Does that match the picture? Can we just trust the signs? What direction was that thing rotating? Well, actually, I have this right. It's rotating positively. So now I'm going, crap. You see what I mean? Like, this is why this is a problem. And again, the only way you picture that is from the previous part of this drawing when I erased it, but we said first C went up to there, and then the whole thing had to rotate in that direction. So that's why I know I have this arrow going the right direction. So now I'm like annoyed because that isn't going to work unless I'm not going to kind of get the right answer to this, unless I go back here and kind of get rid of that sign and say it's actually positive. That makes a difference. Like, what direction is it rotating? Like, it's great to know the speed, but it's like, God, you don't know the direction, right? That seems stupid. And so now I'm back to thinking, this is why I hate the sign thing, or this is why this is kind of a problem. So all I want to do next time is just play with this some more, and just keep giving you examples. And there's kind of there's one other way to do these problems that we'll get to at some point, but it isn't any less work. It's just kind of a cool thing to think about. But the only thing I would like you to take away, I guess, is just the fact that all of these are dictated by that equation and splitting things into X's and Y's. And we got a little bit of an issue with the sign that we got to kind of sort out a little bit. But we're well on our way. All right. Get out of here and we'll talk more on Thursday.
Can I ask like one or maybe two more questions before we're gonna leave?
Certainly.
Okay, so you call it a stroke, right? Right after the explosion happens in the piston, and it just goes down and up, right?
Yeah.
Yeah. So to have a longer stroke, you have to increase the radius of the shaft. Is that how it works?
You mean the radius of the?
Of the actual, or is that the shaft? Is that how they call it? Or whatever, how far is it? Yeah, like that, from driver to center distance.
Yeah, it's really yeah, exactly. It's the green line. Like that's what you've got to have. So it's actually a combination of the radius, the blue line over here, the radius of that, because if that's a much smaller circle, then this isn't going to move much back and forth, right? So it's kind of related to this, but isn't it also related to that crank arm, like how far away that is? And so it's a combination of both those things actually, because the technical definition of stroke is the distance from A to B. In other words, how far does that thing actually move? That's what stroke is. It's a distance. It's maximum change of the piston inside the cylinder. So no, logically, and again, I'm saying logically because I'm thinking about this out loud, it's a combination of the blue length and the green length.
Okay, and the other question, because we found this velocity c of x in x direction,
Yep.
and if you're gonna look at the velocity b into x direction,
E.
yeah, from
Okay.
this last question,
Yep.
they should be like a little bit similar, because it seems like velocity c into x direction is like small, like a little bit too small, no?
Yeah, okay, I see where you're going with that. So let's see if I take, what do we say, velocity of B? Do we ever even write that down somewhere?
Velocity of b in x direction was like around 7.25.
Yeah, correct. So it's like 7.25. That's exactly right.
And after, if you're looking at the velocity c in x direction, it's like only 2.42.
Yeah, so that's bothering me conceptually. I completely agree with that. Well, as I mentioned before, with respect to signs, this is a place where the signs are really kind of in our last answer, like for the rotational speed, it didn't matter. It's like, okay, well, it's positive, it's negative. At least we got the number right. You know what I'm saying? Like we said it does matter because it's like direction matters, but at least we got the number right. Well, if we take this 5.89 up here and we leave it positive, as we were just kind of feeling like it should be left in this angular velocity down here at the bottom, we said, well, really, that should be positive so that this comes out positive, or this doesn't really make any sense. Well, if we go back here and say, okay, fine, we'll leave that positive. Well, if you put this back up in here and it's positive, then that answer turns out to be like 12 meters a second. So the question is, which one is it? Is it 2 or is it 12? And
I mean, if you're gonna think about this, you really want to have the velocity smaller at the piston and bigger velocity at the crankshaft to gain more power, right? That's gonna be a perfect
Oh gosh.
setup.
it's kind of the whipping effect too of something. You know, it's kind of like if I have this pen in my hand right here, if I had a rope on the end of it with a little ball on the end and I whipped it, like I can really generate a ton of velocity on the ball that's hanging on the end of the string, you know, like a trebuchet, if you will. So even though I have a rotational speed to the pen, the rotational speed on the ball is way faster. And so it's sometimes tough to conceptualize because it sort of depends on where B is and it's spinning around in circles. Where is that thing right now? So again, I personally find this consternating. Like I sort of feel like if I'm in Reno right now and you know, again, it's embarrassing to say this, but you know, is the right answer to this 2 or is it 12? Oh, man, I'm not 100% sure because I see all these contradictions in the sign.
But you said that pretty much like the A and B is going to be a driver, right? So that's what makes the things go, and C is just follows whatever B does.
That's correct. And to your point that this thing is moving 7 to the right, it just feels like, really, would this thing only be moving 2? It just doesn't feel right, does it?
Hmm.
But neither does 12.
Yeah.
But that's because of the whipping effect. Does that make sense? In other words, this BC arm is rotating too, and that's kicking into this process down here, isn't it? And if I'm a betting man, I'm feeling like, well, this thing was wanting to move right 7 down here, right? It's wanting to move right 7, but then this thing is rotating, whipping, and increasing that speed, and so it feels more like this should be the 12 answer, doesn't it?
Yep.
But then, okay, fine. But that doesn't work for this equation right here, because 8.25 sine of 25 can't add to a positive number and get 0. Since C isn't moving vertically, we have to make sure that this moving up, because we said up here this was actually moving up, right? And that means down here this is going to have to be moving down to counteract that. So it's kind of like this thing definitely wants to be negative, and so now all of a sudden it's like, well, now that's a contradiction. And so but I actually want you to feel that a little bit before we entirely solve it.
I just want to know what's right and what's wrong. That's it.
Oh gosh.
So yeah, let's I want you to soak on that a bit. And I have a few more things I want to think about it too, because in some respects, I'm actually looking what I've done before and thinking, did I just oversimplify that or like not think it through? I've always found it to be the case. If you wade in further, it's like, oh, that makes sense. I get that now. Should always be able to do that. All right, I got to meet somebody, so I will see you guys on Thursday, and I'll have an answer, or you'll have an
Thursday,
answer.
Doug.
All right, see you guys.
Yeah.